Welcome to Cosmology Talks, everyone. Today we have Adrien, who is a PhD student at the IJC lab, Colin Hill, who is an assistant professor at Columbia University and associate research scientist at Flatiron Institute. And we also have Evan McDonough, who is an assistant professor at the University of Winnipeg and director-elect at Winnipeg Institute for Theoretical Physics. Today they're talking about all things early dark energy, in fact, talking about 3 different papers, but we expect that they'll be able to tell a coherent, interesting story about them together. So Colin will start talking about the perplexing state of evidence for and against early dark energy in Planck and ACT. Adrien will follow up with a similar talk, but involving SPT as well. And Evan will close talking about some early dark energy model building, trying to not just achieve consistency with the CMB, but also large-scale structure. Fans of the channel for a while will remember Colin's earlier talk, talking about how early dark energy might make H Naught better, but makes S8 or the situation with large-scale structure worse. So Evan's job is not an easy one. So welcome to Cosmology Talks, Adrien, Colin, and Evan. And Colin, do you want to start by telling us briefly about your paper?
So a quick summary of this paper is that we analyzed early dark energy models that are of interest for yielding a higher value of H Naught from analysis of CMB data, in particular using the latest data from the Atacama Cosmology Telescope, ACT, and that was the DR4 data release 4 data set from ACT, which came out in 2020. And we had not used that data previously. Well, no one had used that data previously to analyze this early dark energy scenario. We didn't attempt to do a global analysis fitting all cosmological data sets in this work, but really we're focusing predominantly on whether the analysis of different CMB data sets yielded consistent results. So in particular, if we replace Planck with ACT or ACT plus some low L data to fill in modes that we don't measure on large scales, then do we get the same results for the EDE scenario? And interestingly, we got somewhat different results at the sort of 2 to 3 sigma level. So ACT is consistent with allowing a non-zero amount of early dark energy, whereas Planck disfavors that. It's an interesting situation, and what's exciting is that we have much better data that we're currently analyzing within ACT, which should let us make a much, let's say, firmer conclusion later this year, hopefully.
If there was only one thing people remember from the paper in this video 6 months from now, what would you want it to be?
A brief takeaway really is that the ACT DR4 data don't exclude the EDE scenario. The data are consistent with a non-zero amount of EDE, which can indeed yield a higher value of H Naught from the CMB. Again, that's without including any local H Naught data in the fit, so that's quite interesting. This is in contrast to what we see from Planck, which does not prefer non-zero EDE. And if we do a full analysis of both Planck plus ACT, then the Planck data still carry enough statistical weight that it drives the EDE fit back towards 0. So we're hard at work trying to understand some of the subtleties between Planck and ACT at the level of the data itself. But the one most important thing to take away is that we have much, much more powerful data already on hand from ACT. And in about a year's time, we should have a much clearer handle on this situation. So stay tuned for that.
But at the moment, any analysis you've done has been done blind, so we can't try and read your poker face about.
Everything's blinded. Yeah. We haven't actually looked at any cosmological parameters yet from the internal ACT analysis.
Okay, so do you want to go into the background now?
So just to put this in context a little bit, I'm sure regular viewers of this channel are aware of the Hubble situation or Hubble tension. Without going through all the measurements, my personal view is that the observational situation is still a bit muddy, but I think it's a very exciting situation to be in because it's led us to think about all sorts of new physics in cosmology that we probably wouldn't have thought about otherwise. Most of the sort of well-motivated quote-unquote extensions of Lambda Cdm have returned null results, and this particular channel, if you will, wasn't something that people expected to see new physics in maybe 10 years ago. So we want to change the cosmological model in some way that the value of H Naught that we infer from the CMB or large-scale structure data is increased. So one might think that we could solve this problem by changing cosmology at late times, for example, changing the dark energy equation of state, but such scenarios are very, very highly constrained by the fact that we've measured the relative expansion history of the universe and the growth of structure to some extent at late times very precisely. So this is a plot showing the expansion history measured from BAO distance measurements, where here you can divide out an overall calibration factor, which would be H Naught, and just look at the relative expansion history as a function of time. And you can see that we have very tight constraints on that. So you can't put in lots of crazy evolution in the dark energy equation of state and use that to try to solve the H Naught tension.
Just a quick question about this slide. I guess this particular slide would leave scope for something happening less than redshift of 0.15, but the supernovae themselves kind of evolve like Lambda Cdm in that range. Is that right?
Yeah, there's been a couple of papers about this from Evstathiou and other people pointing out that even attempts to put in strange features at very low redshift, actually, if you do the analysis self-consistently, including the full likelihood from shoes plus supernovae, i.e. not just an H naught prior, then even such very, let's say, fine-tuned models with features at super low redshifts are also inconsistent. So there's really no wiggle room. Good. Yeah. So I think I said this. So as Lloyd Knox and Marius Malaya pointed out in this nice paper a couple of years ago, probably the most interesting place to look for solutions to this problem is in early times, just prior to recombination in particular.
Oh, the least unlikely,
Okay.
right?
Yeah. The phrasing here is important. It's a hard problem. So we don't have a single model that's the clear, let's say, most highly motivated one that's going to solve the problem. But this class of solutions is, I think, the least unlikely to be successful. So a generic consequence of this is that there's new signals in the cosmic microwave background, which then motivates everything else that we're going to talk about here. So just to give you a flavor of the ACT data, why are we still measuring the CMB post-Planck? So this is actually a patch of sky from Planck data at 143 gigahertz. So if you flip between this and the next slide, here's what it looks like once we combine with ACT data. Hopefully people can see this in the high resolution version. So you'll notice that the small scale features of the CMB just pop into focus with the high resolution and low noise of ACT. Of course, SPT has similar high resolution, low noise data as well on a smaller patch of sky. We can see all these other features in the small scale millimeter wave sky, radio and infrared point sources, which are these positive red spots, as well as the shadows that are cast in the CMB from the thermalized Z effect. And that's these blue, little blue spots that you see in the SZ clusters. So there's all sorts of cool information in these high resolution maps that we can make from ACT. I'm just going to talk, of course, about the CMB power spectrum today. This shows our foreground marginalized CMB power spectra from ACT DR4, skipping past many years of work by many dozens of people who are very much crucial to the success of everything we're doing. So up top is the TT power spectrum. The EE power spectrum polarization is in the middle. We have a moderate detection of lensing B modes down there as well, and then the TE cross correlation in the bottom panel. So one thing to point out immediately you can notice is that we don't measure the largest angular scales in the temperature sky, and that's because of atmospheric noise that contaminates our measurements from the ground. So it's advantageous for us to combine with space-based measurements that cover the largest angular scales, which could come from WMAP, for example, or a slice of the Planck data set that just looks at the large scales. WMAP and Planck are completely consistent with each other at the level of the maps and the data points themselves at these large angular scales. This is just a compendium showing the status of the field circa, I think, summer 2020. We have this beautiful set of measurements covering a very wide range of angular scales in both temperature and polarization from a wide variety of experiments at different sites. And this simple model, this is Lambda Cdm shown here, provides a great fit to these data. So any deviation that we're talking about in terms of new physics here is a very small change with respect to this theoretical model. So just to give you a flavor of the challenge that's at hand. All right, so then let's proceed. This is then a summary of the H Naught situation from Lambda Cdm, from the CMB and large scale structure versus local probes. So I'm just showing a very small selection of measurements here. Planck up at the top, ACT plus WMAP in the second data point, SPT, and then large-scale structure measurements from BOSS. And you can see that the cosmological indirect measurements within Lambda CDM tend to come out lower than these local measurements. Formally, the tension between ACT plus WMAP and the latest shoes measurement is 3.4 sigma, but we do have agreement with the TRGB measurements from Friedman et al. So this is why I would say the observational situation to me still seems a little bit muddy, but clearly this motivates thinking about physics that could reconcile this difference.
But why is it muddy if you say ACT plus WMAP, that you're kind of deliberately then ignoring Planck and EBOS?
Oh, no, I didn't mean that. The only reason that we looked at ACT plus WMAP here is that one of the goals of the DR4 analysis was to try to obtain an early universe CMB-based H Naught measurement that was completely independent of the Planck data set, to remove any possibility that systematics and CMB data could be driving this. And the fact that those first two data points and the third data point agree tells you that from the CMB, systematics clearly can't be playing a significant role in this tension. But it's, of course, very exciting that there's a lot of excellent local measurements that are going to continue to improve in the next couple of years. So the situation should be clarified. Okay, so let me provide a quick introduction to the physics of early dark energy. So the idea here is that we want to increase the value of H naught inferred from the CMB. And the way that we're going to do this is by decreasing the physical size of the sound horizon that's imprinted in the CMB. So just as a reminder, the sound horizon at last scattering is given by this integral of the sound speed in the primordial plasma times dt over AFT, where AFT is the scale factor. And if you rewrite this as an integral over redshift like we do in cosmology, then it looks like this expression on the right-hand side. Within Lambda Cdm, the relevant ingredients that determine the sound horizon are just the physical densities of the different constituents of the universe at early times: baryons, dark matter, neutrinos, and photons. And of course, we have a handle on those numbers, in some cases from ancillary measurements, like the phi-RAS measurement of the CMB temperature, Big Bang nucleosynthesis, etc. But also the detailed peak structure of the CMB itself tells us about these densities. So then, given those densities, one can back out H naught effectively just from the fact that we measure the angular size of the sound horizon, theta s star, very, very precisely. It's just the inverse of the peak spacing in the CMB. Good. And so then the ratio, essentially, of the physical sound horizon to its angular size gives you the angular diameter distance. And of course, that depends directly on H naught inversely. So within the EDE scenario, the idea is that we're going to introduce some additional parameters that change the calculation of the sound horizon imprinted in CMB. So in particular, we'll decrease the size of the sound horizon, which then requires increasing H naught in order to decrease dA star, so as to keep the measured value theta s star fixed, because that's measured at extremely high precision in CMB data.
When you said on the previous slide, which is still here on this slide, that okay, omega B, omega M, etc., have been measured precisely by the CMB. I guess the phi-RAS measurement is still crucial to know, I guess, the age of the universe, to know how far we are since the CMB. Is that?
I would think of the phi-RAS measurement really as telling us about the density of the photons, right?
But that's the density of the photons today, whereas the CMB tells us about the density of the photons then.
Well, the measurements of the anisotropies of the CMB don't tell us too much about the average energy density of the radiation. I mean, there's some dependence of the decoupling time, but if we didn't have the phi-RAS measurement, for example, it would be very difficult, in fact, it'd be impossible to interpret the measurements of the anisotropies at the level of determining an overall amplitude, for example. We wouldn't know what AS, the scalar amplitude, was if we didn't have phi-RAS, because there'd be a direct degeneracy between the monopole energy density and the amplitude of scalar fluctuations. So yeah, phi-RAS is super important, which we take for granted nowadays, 30 years later. But if we didn't have phi-RAS, cosmology would be in a very difficult spot.
And it's not, this is completely off topic, but it's not as simple as just phi-RAS made some zero error in the temperature, and that's the H naught tension.
There's a very nice paper about this from Misha Ivanov and collaborators a year or two ago now, called T naught or H naught tension. So I encourage you to read that. If you throw away the phi-RAS data, then you can kind of make things work such that you shift T naught in a way that partially resolves the tension. But if you take Planck plus BAO, you actually do have some sensitivity to T naught coming from late time effects like ISW and CMB lensing, which break this degeneracy that exists in the primary CMB power spectrum, such that it does favor a value of T naught that's consistent with phi-RAS, but with much larger error bars. And of course, as soon as you put in the phi-RAS data, then all possibilities along these lines are kind of lost. But it's a really nice paper. I encourage you to take a look at that.
I don't remember whether you said it, but phi-RAS was, of course, the spectrometer on COBE that measured the intensity at so many frequencies that it got the full black body spectrum, whereas Planck and others measured it at a smaller number.
But crucially, it's an absolutely calibrated instrument. So it's actually a very different architecture than what we've flown on WMAP or Planck, or what we use for measurements like ACT and SPT. So measurements like WMAP and Planck are actually entirely relative. There's not an absolute reference source or load on board the spacecraft. You're never comparing the temperature of the sky or the intensity of the sky to some reference load. So what we have to do actually fundamentally is to calibrate all of our measurements ultimately back to the phi-RAS data, whereas phi-RAS data have such a reference load on board. Okay, so how do we implement this EDE component? We're going to use a model here and in the subsequent talks as well, based on a new pseudoscalar field phi. The idea is that this field has some potential such that it's initially frozen on that potential due to Hubble friction. So if you look at the Klein-Gordon equation and expanding universe down here at the bottom, there's this frictional term 3h phi dot, and initially the Hubble parameter has a value that's much, much larger than the characteristic mass or curvature of this potential. And in that case, the field is just frozen by that frictional term. So it's just stuck there. and it looks like another contribution to the cosmological constant, or dark energy. So the Hubble parameter drops below the mass of the field at some point and then rolls down the potential and oscillates around the minimum, and the effective equation of state then depends on the exact shape of the potential. To put in some numbers, if you want to have a significant change to the sound horizon, you need the field to start rolling sometime between, say, redshift 1,000 and 10,000, and then that tells you that the mass of the field has to be of order 10 to the minus 27 electron volts. So it's much, much lighter than anything in the standard model. Okay, so then the final phenomenological point to consider is that we need this new component to go away faster than matter at late times. We don't want this thing to stick around because then it will mess up late time cosmology. So we end up having to tune the shape of the potential a bit such that its effective equation of state W at late times is greater than 0. I write down the canonical type of potential that we're going to consider, which looks like a axion 1 minus cosine of phi, but raised to a higher power to the n, where n is greater than or equal to 2 in order to satisfy the phenomenological considerations above. So this equation down here at the bottom, W equals n minus 1 over n plus 1, gives you the late time equation of state. So you can see easily that we need to have at least n equals 2 in order to satisfy that if you want integer values of n. We're going to fix n equals 3 for all of the analysis that's done here, as this has been found to work pretty well with current data, but we could have used 2, 3, 4. On the next slide, then I have a plot that's going to be really useful to think about the parameterization of the model. So we could have parameterized it in terms of these scalar field parameters like the mass, the decay constant, F, etc. But for analyzing data, it's important to use a parameterization that's connected to observables. So this plot shows the fraction of the cosmic energy budget that's stored in the form of this EDE as a function of redshift. And the parameters that we're going to use are first the maximal contribution that this ever makes, so the peak of this curve, FEDE, at some critical redshift ZC where that peaks. And we'll just refer to that as FEDE. And then the final parameter that we need in addition to those two is the initial starting position on the potential, theta I. So we have these 3 additional parameters beyond Lambda Cdm. So the reason that this model is interesting is that if you run a calculation of the CMB power spectrum in this model, which is shown in red, versus in Lambda Cdm, which is shown in black, then you can find models where you get H naught of order 72, which look indistinguishable within 1% difference, shown on the right panel, compared to a Lambda Cdm model with a H naught of order 68. So that's obviously quite interesting. The physics is really exactly what I told you a minute ago with the decrease in the sound horizon. It is important to treat the perturbations in this EDE component correctly in order to get this power spectrum right. So that was one subtlety that I think a couple of years ago had to be solved. Okay, then the next slide shows a similar calculation of the matter power spectrum. These are the exact same models I just showed you on the previous slide, but now in contrast, you can see a difference between these two models, even on this huge log scale on the left panel. If you look at the ratio in the right panel, you can see that there are sort of 5 to 10% differences in the matter power spectrum across a range of scales that are well measured in current data. You might wonder what's driving this. Is it related to the EDE parameters or something else? It's actually the shifts in the Lambda Cdm parameters, things like the cold dark matter density and the scalar spectral index NS, which have to change that lead to this effect on the matter power spectrum. And that propagates to an increase in this S8 parameter. And a couple of years ago, Evan and I and collaborators looked into this in some detail. And this does remain an issue, even in the results that I'll show you in a few minutes from ACT.
And you actually gave a nice talk on the channel on this, so people can check that out.
Indeed, yeah, there's a lot more detail in there. All right, so now let's run through some of the constraints. So first to warm up, here's the results from Planck data alone, which we looked at a couple of years ago. So if you just analyze Planck alone, Planck doesn't prefer a non-zero value of this FEDE. The posterior on the amount, this top left panel up here peaks exactly at 0, and you just get an upper bound. The error bars are relatively large, coming from just fitting this one data set, but it's still a meaningful constraint. And as you can see, H naught, shown down here in the middle, remains in some tension with shoes.
And the phrase Planck primary CMB means temperature TT, TE, EE, but not lensing?
No lensing, that's right. Yeah, just TT, TE, EE.
And just to be completely precise, when you say no lensing, you mean no reconstructed lensing potential power spectrum, but of course one is taking into account the effect of lensing on the primary CMB.
That's right. There is a little bit of lensing information in the 2-point function as well. We don't try to remove that somehow. So we looked at a whole bunch of different data set combinations in 2020 and 2021. So I'm just going to show you the most constraining one that we had prior to the ACT analysis. So this is looking at Planck plus the effective field theory likelihood for the BOSS data constructed from Misha Ivanov, Mark Simonovich, Matthias Aldariaga, and collaborators. and then constraints on S8 from these weak lensing surveys listed up here. So the FEDE parameter is now in the middle down here. And if you look at the blue curve, that's what we get after we fold in this large scale structure data in addition to Planck. And as you can see, the posterior really tightens up towards 0. And we got a pretty tight upper bound, FEDE less than 0.05 at 95% confidence. So without including any local H naught measurements, if you just ask the question, did this cosmological data alone prefer the existence of EDE? It doesn't, as of summer 2020. And accordingly, H naught does not go upwards, and there's still some pretty significant tension with the shoes measurements.
Yeah, I guess it doesn't go upwards, and the error bars are still quite small, even though you've allowed early dark energy.
Yeah, that's right. Once you combine with the large-scale structure data in particular, you get a pretty tight constraint on H naught by breaking various degeneracies. So I think this is just a quick summary of everything I told you a minute ago. This third point is kind of the important one, which is that if you want to increase H naught using this EDE scenario, you have to add more early dark energy, but then that leads to an increase in the cold dark matter density, NS, sigma 8, S8, and then that worsens the fit to large scale structure data. So I think Evan coined this term of tension trading, where you're improving things a little bit for H naught, but then worsening things for S8. So there's some lack of concordance that's seen here. And I should note the reason that these other parameters change, like the cold dark matter density, that's just because of the fact that this EDE acts to slightly suppress the growth of perturbations just prior to recombination when it's active, and you have to compensate that suppression. This is an early ISW effect. To compensate that, the model prefers to increase the amount of cold dark matter. Okay, so now let me talk to you about the ACT results. So this is all set up for where things stood circa late 2020 when we started to look at this. So in this analysis, we really want to answer a narrow question, which was how robust these constraints on the EDE scenario are to the choice of CMB data set that's used. So what do we find if we replace Planck with ACT or ACT plus WMAP or some other low TT likelihood to fill in those missing modes that I showed you in the power spectrum a while ago? Within Lambda Cdm, we had found that ACT and Planck were consistent at the 2.5 sigma level. How consistent are they in this EDE scenario? Consistency in one parameter space doesn't guarantee consistency in another parameter space. So here's the list of the likelihoods that we used. For boring technical reasons, we used a subset of the Planck TT data instead of WMAP itself, but they're essentially identical. And then we consider a little bit of additional data to break degeneracy, so BAO distances, and then Planck CMB lensing.
You said one thing, that just because they're consistent in one doesn't mean that they'll be consistent in the other. I guess the early dark energy parameter being 0 is a subset of the early dark energy model. So at worst it'll be 2.5 sigma consistent, right?
If you put in, or you could imagine the following context. I'm not saying this is not the analysis they did, but put in a shoes prior on H naught, or any data that strongly prefer the larger H naught. It pulls you to one region of parameter space. And in that region of parameter space, the tension could be whatever it is.
But that's adding new data. This is just making a model that has more parameter space.
But that model has more parameter space, and different regions of that parameter space may fit different data sets differently. So you have different compensations occurring in the fit to a combined data set. You're like trading the chi-squared, so how much, to the extent to which the model is fitting one data set versus another data set. So you could easily, I think, drive up ostensibly the tension with one data set while fitting something else really, really good. And it does have to do with these expanded parameter spaces where new sort of islands open up that provide a good fit to the joint data set, but exhibit different relative goodness of fits.
Yeah, another way of saying this, suppose that we ran some model where ACT preferred the existence of some new non-Lambda Cdm parameter at 20 sigma and Planck completely disfavored it. Then within the context of that parameter space, you'd get a big inconsistency, even if in Lambda Cdm they were consistent at 2.5 sigma. That's just a toy setup, but that's the idea. Okay, so here's the first taste of the results. So the green posteriors here are the Planck only results I showed you a minute ago. As usual, this is the 3 FEDE parameters in the top 3 panels, and then H naught and S8. And then the ACT results are in red. So if we look at FEDE first in the top left, you can immediately see that there is a mild preference for this to peak away from 0, whereas the Planck posterior peaks right at 0. So that's a bit interesting. Accordingly, H naught goes up as one anticipates by design. But from ACT alone, the error bars are quite large. So it's hard to draw sharp conclusions. So the next slide is the results with the low L Planck TT data folded in. The blue posteriors here are the results that we get with ACT plus this WMAP-like subset of Planck included. And interestingly, although the error bars shrink, the posteriors tighten up significantly, the preference for this non-zero value of FEDE does not go away. The posterior in the top left there stays peaked at a non-zero value. And formally, the results here for the marginalized constraints on FEDE, are inconsistent with zero at more than 99% confidence. So there's one subtlety here, which is that if you're only fitting CMB data, then you still have this large so-called geometric degeneracy that involves the matter density. And that goes back to the 90s when people identified this. So it's really advantageous to combine with some ancillary data that breaks that degeneracy, and BAO and CMB lensing do that extraordinarily well. And once you do that, it shifts your omega M up into a higher region such that S8 then gets pulled upwards. So the red and the blue, if you look at the bottom right there, they do have a consistent posterior with S8, but the error bars are massive because of this geometric degeneracy. And so you really want to look at this after including BAO data. And in that case, the tension comes back up as we had identified in the earlier work. Yeah, so then the final takeaway on this really is that even after including the BAO and CMB lensing data, that the top left posterior on FEDE is still peaked away from zero. H Naught comes in at 71, and we see some non-negligible preference, I would say, for the EDE. But if we then take a step back and say, what about if we use the full Planck data set in the analysis? So let's do full Planck data plus ACT. Then this preference for the EDE, mild as it is, goes away, and the posterior on FEDE in the top left up there in orange peaks again right at zero. And this is just coming from the fact that the overall constraining power here in this combination is still dominated by Planck. The Planck data set carries more statistical weight than anything else in cosmology. So yeah, there's some, let's say, tension there between what ACT prefers in this model versus what Planck prefers. And uncovering that is the focus of some ongoing work.
Okay. I was just going to ask one quick question about how dependent your results are on n equaling 3. Because that's not something that was varied.
Yeah, we ran some test runs for the paper, which you can find the details of, with n equals 2. And in that case, the results still look very similar to what we found here with n equals 3.
And 4, 5, 6, 7, 8, 100, 200, they don't get better?
I don't think you can make n arbitrarily large. I think you go up to something like 5-ish before things start to get a little bit weird. In the Smith et al. Paper from 2019 or 2020, they looked at this a little bit and find that roughly the range from 2 to 5 seems plausible. We after we had found these results, you can imagine we wanted to understand at least at some level where this was coming from in our data. So what I'm showing you here are residual plots. So the data points here are the ACT-DR4 data, and then the models that are shown, which look almost indistinguishable by eye, are the best fit Lambda Cdm model to ACT or the best fit EDE model. The residuals in the middle panels are in dark blue for Lambda Cdm and in light blue for EDE. So if you look at this, TT, TE, EE, you see almost no difference with the exception of the bottom panel. I've highlighted the few points that contribute all of the delta chi-squared. It's just these lowest 7 bins in the EE power spectrum where you see that the blue, the light blue points, tighten up towards 0, which tells you the residuals are smaller. So the EDE is providing a better fit there. And that's where all of the delta chi-squared comes from in the fit to ACT. So that contributes delta chi-squared of about -9, which is a preference on the order of 2 sigma. So within ACT alone, that's where this is coming from. Obviously, it gives us a little bit of pause to see such a localized feature that drives the preference. And in fact, if you divide this up further, we found that feature only exists in one of our patches of data, the so-called wide patch. So that makes us worry a little bit. The next slide shows similar residuals for the fit to ACT plus this low LTT data from Planck. And here, so you still see that same feature in low LEE, but there's also this coherent difference that you see in the TE power spectrum now, where if you look in this middle panel, you can see that there's a wide range of Ls for which you have this coherent additive difference between the best fit Lambda Cdm, best fit EDE models. And that TE sort of, let's say, issue had been seen before in the ACT-DR4 Lambda Cdm analysis. And it turned out that the EDE model could really sort of mop up that difference. It then drives this additional delta chi-squared that leads to something like a 3-ish sigma preference for the EDE model over Lambda Cdm. So I'll start with just the experimental takeaways. So obviously seeing this is now leading us to really investigate a comparison to the ACT and Planck data as much as we can at the level of the maps and the power spectrum data points, so without making reference to any theoretical model. And that's ongoing work. Some of the systematics that these features I just pointed you to might lead us to worry about include the transfer function of the data, ground pickup. So there's mountains in the far side lobes of our beam. We do a lot of null tests and other robustness checks to validate against these kinds of issues. There's many dozens and dozens of pages and hundreds of null tests that are done before we unblind and look at parameters. But a subtle tiny feature like the one in EE there could be just below the threshold of our null tests and then partially drive some of this preference. So there's a lot of work ongoing to try to check these sorts of things as much as we can. On the theory side, perhaps I'll leave Evan to talk more about the theoretical situation, but the best fit EDE model that we find with the ACT data is a little bit different than some of the qualitative ideas that we had thought about before. So in particular, the critical redshift seems like maybe it's actually below matter radiation equality, but the error bars are still pretty large. Another interesting fact is that the initial displacement of the potential is consistent with being quite small. And in that case, you could maybe just use a monomial potential rather than these 1 minus cosines. Good. And then lastly, I'll just note that I didn't quote some sort of tension between ACT and Planck in some units of sigmas, and that's because these posteriors are so non-Gaussian that that's almost meaningless. So there's some interesting work that's been done in the last few years related to non-Gaussian tension metrics, like the suspiciousness that DES has used. And I think it'd be interesting to try to apply some of those to this problem.
I thought when people quoted sigma for a non-Gaussian, it was just a p-value that was converted into an equivalent Gaussian p-value. Is it not that simple?
Yeah, but when you have a multidimensional parameter space and you're trying to quote some overall single number, then I think you have to be cautious doing things like that.
Oh, sure. But I mean, there's a million different ways you can do it, and you can pick which one a priori you found the most interesting. I guess the a priori being the crucial part.
Yeah, I'll just say we haven't tried to do that at the moment. So the quantification so far has been at the level of essentially frequentist tests comparing the chi-square to the best fit models.
Okay, cool. I guess at this point, there's a sort of an elephant in the room, which is that you've analyzed ACT and Planck, and there's another CMB experiment out there with comparably good data to ACT. So maybe this is a good point for Adrien to take over, and you can tell us what you did that is described in your paper.
In this paper, we focused on continuing the work done with ACT-DR4 data concerning the early dark energy model to see if we can also observe this hint in favor of non-zero early dark energy in another independent experiment that is observing the CMB, which is the Southpaw Telescope.
Cool. And if there was only one thing that people remember from this talk, what would you want that to be?
I think it will probably be the fact that SPT3G data alone are not as constraining as Planck and ACT DR4 data on this particular early dark energy model, but the results found with SPT3G do not rule out the hint we have seen in ACT. And so the overall conclusion is that we have to wait for better data sets to learn more about this particular model.
And are there better data sets on the way from SPT?
I'm not part of the SPT collaboration. I am part of the ACT collaboration as well as Colin. We are using public data and also a public version of the SPT3G likelihood available.
Okay, well, Colin's talk provided quite a good intro to you, but if there's anything more that you feel is still unsaid about why you did your analysis, feel free to say it.
As Colin said, everything starts from the H Naught tension. And of course, my talk also starts with this famous plot that illustrates the tension between the CMB-based measurement of the Hubble expansion rate and the measurements done using supernovae calibrated with Cepheid stars. But I would like to focus a bit more on the potential solutions on the CMB side for this tension. And one of them is that there could be some systematics in CMB data. Colin quickly said that this is unlikely because we have independent measurements, and I will quickly talk about some studies we've performed to check the presence of systematics in CMB data. And then the second option is obviously physics beyond the standard model, and in particular the early dark energy model, and I will discuss that a bit after. So yes, I will focus on the first point, that systematics in the CMB. Basically, when we do a measurement of the CMB, we want to recover this true value of the anisotropy on the sky, but our measurement, our observed anisotropies, are convolved with some instrumental effects, such as calibration amplitudes, polarization efficiency, beams, that account for the finite angular resolution of our instruments, or some transfer functions that arise from filtering operations we apply on the maps. And from that, in order to extract the cosmology from these measurements, we compute the power spectra, and the convolution in real space become multiplicative effects in harmonic space, and we will obtain some biased power spectra and then a biased cosmology. And the idea behind that, and we've worked on that last year with people from my lab, is to build observables that are less sensitive to systematics. And for this observable, which is RLTE, the correlation coefficient between T and E modes, this particular observable is insensitive to multiplicative effects. You see on the left, if you compute the correlation coefficient with the observed power spectra, every instrumental effect will vanish and you will recover the true correlation coefficient measured. And we have applied this kind of analysis on Planck data in particular, and we obtain an estimate of the correlation coefficient for Planck data in red here. And here we compare it with the best fit obtained from a standard power spectra based analysis. In the bottom panel, you can see that everything is very consistent here. So consistent with the standard analysis. And if we go a step further, and if we look at the cosmological parameters themselves, you observe the constraints from the correlation coefficient in red compared to the standard constraint from Planck in blue. And the first conclusion is that we have constraints that are fully consistent with the constraints from Planck. And of course, we have wider error bars here, but this is the price to pay for having an unbiased measurement of the cosmological parameters, and in particular, H Naught.
And in a sense, you've got less data, right? Because they've got TT, TE, and EE, and you've just got one power spectrum. Is that essentially what's happened, or?
We have a loss of information when we combine these three. For example, with the correlation coefficient, and this is why I can't show the posterior for this parameter, we are not able to constrain the amplitude, AS, very well, because it vanishes in the ratio. If we go back to the Hubble tension, we have added a new point that is kind of robust against a certain kind of systematic effect. And another way of looking at systematics affecting the CMB measurements is to do the exact same measurements independently. Colin has talked about the results from ACT+4, but there is also another experiment, which is the Southpaw Telescope, that has measured the CMB anisotropies. To give a quick description of what is SPT, this is a 10-meter telescope located at the South Pole, which has observed a very small patch of the sky of around 1,500 square degree, very deeply at 3 frequency channels. And then from the Atacama Cosmology Telescope and South Pole Telescope, we are able to give these 2 additional constraints that are independent from Planck on the Hubble expansion rate. And the conclusion is the same as Colin's one, is that it is very unlikely that a systematic can explain this kind of tension, at least a systematic in the CMB. And this is why we focused on physics beyond the standard model, and in particular on the ED scenario. I will give a very quick recap of the results before the SPT3G analysis. So as Colin said, Planck data do not favor very high value of the FED parameter with the following upper limit. But if we combine Planck with additional probes like large-scale structures, probes, and local measurement of the Hubble constant, we obtain a small preference for non-zero FED value. But of course, we want to observe a preference for non-zero FED without assuming any late time prior. And this was done with ACT+4 data, where we observe this preference for non-zero value of FED, along with an improvement of the fit to the data, which is a 2.1 sigma preference in favor of early dark energy. And the thing which is even more surprising is that when we combine ACT with the largest scale from Planck, we observe that we have a larger preference in favor of early dark energy. And given that, since we know that we do not favor early dark energy if we look at Planck data, and we have some hint in favor of early dark energy in ACT data, this status of the ED analysis motivates us to constrain the ED parameters with public SPT3G data.
What are the details when you do this?
I will also be very quick on that because Colin already presented this model, but we used the exact same model and we fixed n to 3 for the reason Colin mentioned. Again, we used the same evolution. The only difference is that we used, in this particular paper, the early dark energy model implemented in CMB instead of class. But it gives results that are totally consistent with the results found with a class Boltzmann solver. And again, as Colin said, the field is initially frozen here. And at early time on this plot, you can see the energy density as a function of redshift, and you see that at early time the field acts as dark energy and starts to oscillate when we reach critical value for the redshift, and then the energy density starts to dilute. Of course, we use the exact same phenomenological parameterization for the field to put constraints on the early dark energy model. And here are the first result for SPT3G compared with the results on Planck and ACT+4. And as I said in introduction, the result is that we do not have the same statistical constraining power on early dark energy with SPT3G. But we are not able to rule out the int seen ACT+4 data. And if we look at some combinations of SPT3G with either the large scale temperature measurements from Planck or large scale structure probes, you see that we improve a bit the constraints on FED, but we still have quite large constraints on this parameter. And we are still consistent with the ACT constraints. And one thing you may notice here is that we have this quite strange posterior distribution for the critical redshift. The reason why we observe that is that we have used wide prior for the critical redshift. Usually in previous studies, the critical redshift was limited between 10 to the 3 and 10 to the 4.3, and we widened this prior a bit. And this is why we see these two degeneracy directions here in the H Naught FED plane. And I will give a bit more detail about that. Here I put the 2D posterior distribution in this plane for SPT3G combined with the largest temperature measurement from Planck and combined with large-scale structures here. And the yellow contours you see are the samples for which we have a lower value of the critical redshift, and the blue contours corresponds to the higher value of the critical redshift. And you clearly see here that we have two degeneracy directions. And one particular takeaway of that is if you look at this particular case, you see that the data seem to prefer quite high value of the critical redshift, resulting in a quite low value of the Hubble expansion rate. And it artificially allows for quite high value of FED, because if you introduce this new species in the universe too early, it won't have a big impact on the size of the sound horizon and then on H Naught. And the important conclusion of that is that looking only at the FED posterior distribution is quite dangerous because it depends on the prior range you use.
Yeah, so is it true that basically the upper extent of this FEDE blue plot is essentially arbitrary? You could make it go larger and larger and larger by allowing Z critical to go larger and larger and larger, because there'd be a bigger fraction and it would dilute away earlier. So therefore, at formation of CMB, it still never gets to dominate. Is that essentially what you're saying?
The chains are quite low to converge. So I haven't tried to widen more the critical redshift prior range, but my guess is that if we open the prior on the right, we will observe that we can't discriminate between 10 to the 5 or 10 to the 7.
So, yeah, exactly. So maybe putting it one more way is that there's these two bumps in the Z critical. One is between 10 to the 3 and 10 to the 4, and that is actually fitting the data better. And then the other bump is essentially just that it's completely unconstrained.
Right. And the last thing we checked in this paper is combinations with other datasets, because we have plenty of datasets available, CMB dataset. And it is interesting to look at the combination between these different probes. We already had a look at the combination of SPT3G with the largest scale from Planck. But if we look at the joint constraint on SPT3G and ACT+4 data, we observe that we recover this preference for non-zero FED value, and we also recover an improvement of the fit at the level of 2.6 sigma, if I remember well. And this is mainly driven by ACT data. And if we combine with Planck, we recover this upper limit. And this particular combination is mainly driven by the constraining power of Planck.
I guess looking at this, the SPT does start to go down a little bit as you get to low FEDE. So it's maybe when you add it to the ACT, increasing. I guess that's why it goes from 2.4 to 2.6 or something sigma. You get an extra couple of 0.1s.
The last thing we checked, that's not in the paper, but we are still working on that, on the model, and understanding things about what's going on with early dark energy, is to try to combine the SPT3G data with a late time prior from shoes. And what we observe is that by doing that, we observed an improvement of the fit to SPT3G data with respect to Lambda Cdm of order minus 6.3. And this is computed only using the CMB part of the likelihood, not considering the improvement of the shoes likelihood, which is a late time prior. So this is quite interesting, and we definitely can't wait to see the future data sets.
Seems if SPT and ACT were all there was and Planck didn't exist, WMAP, I guess, if it did exist but Planck didn't exist, we'd be living in a space where the Nobel Prizes for early dark energy might be on their way out, but Planck does exist, so that's not going to happen.
Just to give a quick conclusion about what I said, this is just what I said in the intro, that unfortunately SPT3G is not as constraining as ACT and Planck on EDE, but we see some degree of early dark energy when combined with shoes with an improvement of the CMB likelihood. And of course, the most encouraging conclusion is that SPT3G data do not rule out the int seen in ACT-DR4 data at the moment.
Did Colin or Evan, do you have any comments on anything?
Or maybe a quick comment on the ZC prior is that if you translate this into priors on the model parameters, so the first paper that Colin and I wrote together, Michael Toomey and Stefan Alexander, we had a section on this, which to be honest, it seems like nobody cares about. The rest of the cosmology community is, what are you doing at the level of particle physics? And it translates to saying that this axion mass is basically fixed to be within a couple orders of magnitude, which is totally arbitrary. And if you widen that range, it's right, it takes them forever to converge because, I mean, in the extreme limit, you can't rule out if there was a phase where FED was 1 at z is 10 to the 15, we just call that inflation, right? But in a sense, you need to impose some upper bound on your prior, but we should keep in mind that this procedure is somewhat ad hoc.
And of course, if there were like 10 different periods of inflation, we wouldn't know that had happened. So we don't even have evidence of the last one. So there could be, FED could have been 1 multiple times.
True. Yeah, I was going to say that this issue about the choice of the ZC prior and how that impacts your posterior and FEDE is the reason why in the ACT paper we decided to quote any preference per se by doing this frequentist test of comparing the best fit chi-squared values, because that's just a pointwise comparison of how well the best fit models fit your data, and then you're not making any statement about the prior range. Because you can basically get any FEDE posterior that you want if you just widen that ZC prior to go up to very high values, as Adrien explained very nicely.
Cool. Well, the stage has been set now for Evan, I suppose. This is the data that the models have to fit. Can you tell us about your recent paper that had a look at that? Actually, just one last thought. The point that you made, Evan, I guess you sort of hinted at it but didn't explicitly say it, but if having this Z-critical prior range very narrow requires quite a narrow mass range of the axion, there is this kind of, even if early dark energy fit the data, all the data perfectly, there'd be this really weird fine-tuning question of like, why on earth this mass happened to have such a value that it had something to do with the decoupling of protons and electrons in the early universe, that right at the time that happened, this mass transition happened. But okay, I mean, it's not like we don't have other fine-tuning things that fit the data well that modern physics is having to deal with. So I don't think that would be a reason to throw that model away.
Right, I think that's a great point. I'm going to talk a little bit about that at the end, I think. Great. So thanks for having me here today. This is really fun to be doing this with you guys. All right, so I'm talking about a recent paper that came out in December. And the basic premise is to take early dark energy, which has some successes and some challenges, and let's promote it to an early dark sector where you have dark energy and dark matter both playing a role, and ask, does that address those same challenges? And so it's a question about the interplay between theory considerations and data considerations. And that's sort of my favorite thing of all to think about. And the take-home message is, can thinking about the theory challenges address the data challenges? The answer is yes, it can. The precise framework that we're thinking about this is this so-called Swampland program, in particular this conjecture known as the Swampland distance conjecture. So this does, in fact, lead to another problem, which is that theory gives you certain priors on what should the parameters of this model be, and the parameters that are preferred by the data are quite different from those. So you're still left with challenges when the model confronts what are the actual theory expectations. So this is sort of the take-home, that we can address the tension with data, but there's still remaining challenges in terms of interpreting this as more than just a toy model, but actually, something that you could derive in a top-down way.
So yeah, in terms of the background, do you want to go into any background that Colin and Adrien haven't covered?
Yeah, I'd like to just briefly reiterate what Colin mentioned about how you fit the CMB in context of EDE. So this necessity for more dark matter, how you can really see this is by add in your early dark energy. You can take our code off of GitHub and toss in some early dark energy into your cosmology. And what happens is, in particular, this first peak of the CMB gets this constant shift. And this has to do with this dark energy is suppressing down your gravitational potential wells. So the amount of redshifting a photon would naively get coming out of a gravitational well is decreased. And then so the net power you have on that angular scale is increased. So in order to weight back down your gravitational potential wells, you need to toss in more dark matter. And just based upon, you have a 10% Hubble tension, and you're adding in order 10% dark energy to address it, you need to add in of order 5% more dark matter. Now, even if you do that, you add in your extra dark matter, you still have this problem that the anisotropies, very small scales, so corresponding to high K, they get adjusted because of this early dark energy. And in particular, there's a modification to this silk damping of the CMB, the damping tail. And it's this near constant offset, which you can fix, just by shifting NS, then you can get a less than 1% change with respect to Lambda Cdm. You can fix this damping tail. I mean, the secret sauce is adding in this more dark matter and then little small adjustments, like raising NS to be pretty close to exactly scale invariant. And then you can have this near perfect fit to the CMB. The second thing that I'll mention in terms of the underlying physics, and this pertains to how well can the model fit the data, is that it has a pretty significant impact on electrical structure, as Colin mentioned. And I guess the things that I would emphasize and reiterate is that the shift in the matter power spectrum is coming from the changes in Lambda Cdm parameters. That's key point one. And key point two is that the impact on the matter power spectrum is actually more severe at higher redshift. So as we get better and better experiments, which are going farther and farther back in time to higher and higher redshifts, the effect of EDE of enhancing the growth of structure gets more and more pronounced. So there's a real prospect for electrical structure experiments to be able to be significantly constraining for early dark energy.
Can you give a quick way of understanding why it's more sensitive at higher redshift? Naively, I'd have thought it wouldn't have made any difference with redshift, so there's some hole in my understanding there.
Yeah, let me think about this. I think it really has to do with the integrated effect of as more modes are entering the horizon. But let me not give you a precise answer right now, and then maybe we can talk about it afterwards and let me think about it more. Unless Colin wants to jump in and say why he thinks.
I mean, it's not too surprising to me that it's redshift dependent, just because you get some integrated effect that comes from, if you have more matter in the universe, then the growth changes as well, right? It's not just an overall change in scale like changing AS would be. Whether it's going to be a bigger effect at redshift 0 or redshift 1, I have less intuition about. There's also some impact coming from the fact that the dark energy density maybe changes a little bit here as well. So it may not be so easily isolatable.
So let me summarize the status of ED and how it fits the data. And in particular, this is the story that was outlined in a couple of papers that Colin and I wrote, and there's another paper by another EFT of LSS group that you can check out. The basic story is that when you fit EDE to data, in particular Planck data, these are posteriors in the fit of EDE to Planck data, which we've seen the nice triangle plots already. It introduces new degeneracies in your model. And you can exploit these new degeneracies to get relatively large values of H naught. And this degeneracy direction between H naught and FEDE, it's in this multi-dimensional parameter space where you're also moving the degeneracy action is also changing the amount of dark matter, and correspondingly this SA parameter, which is this combination of sigma 8 and omega matter. And so if you include electrical structure data, like from dark energy survey or from BOSS, the full shape information using the effective field theory of electrical structure, you can break these degeneracies, and that's where these really tight constraints come from. So the focus of really what I want to talk about today is thinking about that, and then also thinking about where does EDE fit into our landscape of models and quantum field theory and string theory. And again, to flash the same canonical model for early dark energy, let's keep in mind the parameters that are at play. So one, you need this field to oscillate sometime around matter-ration equality, or that number is slightly different when you include ACT, but benchmark value, you need the mass to be or like 10 to the minus 27 electron volts. And the size of the Hubble tension, that's about 10%. Then you can just compare the overall normalization of this potential to H at that time. And you find that the decay constant must be of order M Planck. And this final requirement that basically the EDE does its job and then disappears tells you that this exponent is greater than or equal to 2. And the best fit model that people have found so far is n equals 3. And I think it's an important question that theorists need to grapple with. Can this actually be realized in some controlled and calculable setup? To me, one of the biggest open questions is, how can you get a model with n equals 3? Because the usual expectation is this cosine potential is the leading term in a series expansion.
So in other words, n should be 1, or...
Yeah, so and that's how you get an axion. And there's this huge body of work in the string theory community thinking about, can you get Planckian axion decay constants? And the argument that you can't is because the series should break down. So in this setup, the idea is that you have the terms up to n equals 3, cos phi, cos 2 phi, cos 3 phi are all similar size, and then everything above that goes to 0. And that's how the only way you could identically get n equals 3. So is there an actual physical system or theory, some gauge theory in some setup that could give you this potential? I think is an open, interesting question. So as a starting point to building a more complete theory, we took insight from this set of conjectures about what do 4D models look like that come from some UV complete theory. In particular, thinking about this thing called the Swampland distance conjecture. And so by coupling the early dark energy to dark matter, we're extending it from EDE to EDS. So the theory prediction here is that when in any effective field theory, when you have some scalar field move some Planckian distance, there's at least one other field or set of fields in the theory that get an exponential suppression of their masses due to this. And this is realized in a huge number of examples. For example, Kaluza-Klein modes in any sort of dimensional reduction when you have extra dimensions. So if you parameterize it in this way, some exponential dependence of some mass on this field, you have some parameter C. And the theory prediction is that, say, if phi is decreasing over cosmic evolution, that this parameter should be positive and more, it should be order 1. Our setup is to think, well, what if it's the dark matter which is inheriting this field-dependent mass? And this is the picture we pursued and asked, can taking guidance from the UV complete setups, does that get something for us at the level of confronting the model with data? And so the basic picture is here, where you have the field evolves, times moving from left to right. It's fixed on its potential, and it starts to oscillate. So now you can see the rise in the dark energy and the decay. And now in this setup, you have some dark matter mass, which then gets bumped back up. This is C negative. So the dark matter mass gets heavier when the early dark energy field decays. And now just to jump to the punchline here, it turns out to be the case that if you include a small but negative value of this coupling C, so this dark matter gets heavier around matter-ration equality when the EDE field decays, this can bring the model to simultaneously fit dark energy survey year 3 data, which is in the pink band here, and shoes data. So you can get your CMB and LSS too. But I should caveat that with the data is perfectly happy with C is equal to 0. So you cannot reject the null hypothesis that C is identically 0, only that you can get a good best fit, which seems to be happier than vanilla EDE with both these data sets.
C could be positive, but the initial value of phi could be negative as well, right? On the observational side, that's irrelevant, but on the theory side, is that actually somehow theoretically different, or?
No, these things are identical, because what you should be doing is saying, just put an absolute value. The conjecture is moving in field space some absolute values order m Planck. So you need to pick one branch and evolve self-consistently through there. Right? But the theory would predict that the field should get lighter. Here we're saying the field gets heavier. That's what's important, not what convention we give to the signs of parameters. It's that the field should get lighter when some other field moves a Planckian field distance. So it does get you some mileage with CMB analysis data, but now if you turn back and say, how consistent is this with our starting point where we're taking guidance from? And the conjectures would say this new parameter should be order 1, but all the data says it needs to be less than 0.1. If you take the EDE model as the resolution of your H naught tension, you can ask, how consistent is that with what we think we know about quantum gravity? And there is a mild tension there between the H naught resolving region of parameter space in EDE and the Swampland distance conjecture. So now let's just take a few minutes to get into the weeds just a little bit to understand where those constraints come from. And the key detail here is that when you can go through your cosmological perturbation theory and derive the equation of motion for the evolution of perturbations in your dark matter. And you find a correction term here, which is equivalent to just rescaling Newton's constant. And you're rescaling it by this k-dependent term. And if you think about the limit of high k, and high k here means bigger than the v double prime of the EDE field, it's just a constant shift, a rescaling of g Newton by this factor 1 plus 2c squared, where c is your new parameter. And so the net effect here is that at late times, this enhanced gravitational force increases clustering on both sides. So going C negative, C positive, going in both directions is going to give this extra gravitational force, which is going to bump up parameters like S8.
This is over and above the change in the mass of the dark matter.
Yeah, so on the left here, this is thinking of one mode, one value of K. Look at delta C, and the fractional difference with respect to C equals 0. So you have this, for C negative, you have this swing down, so it's suppressed. Yay. C positive, it swings up. But if you look then what happens subsequent, long after the EDE itself is decayed, but you still have this interaction that lasts from when the CMB is formed to today. And so both of these start increasing. And the net effect is if you scan over values of C, say start from any point, this C equals 0 here, and scan to the left, it decreases and starts increasing again. Instead, go to the right, it just increases monotonically. So you go left or right, you start bumping up SA, and you start basically rooting the fit to the data. And this is the big picture reason why the data does not allow you to go arbitrarily far in either the left or the right. And you get basically this constraint that it's less than order of magnitude 0.1.
And this change of G effective would be a change just for the G effective for the dark matter, or would we?
Right, exactly. So it's like a dark matter philic fifth force. In dark matter community, we would usually say this is some light mediator. So it's a very light mediator for.
And there's no measurement of G Newton with just dark matter that's accurate enough.
Exactly.
Because all of our accurate measurements of that are like balls of lead and stuff.
Yeah, so you need a ball of lead dark matter if you wanted to do that. Yeah. So before I conclude here, I want to just talk about how the different data sets enter into this. So we did consider including the ACT data into our analysis here. And so the blue is what I'd say is our baseline data set of Planck, BAO, and Shoes, and Pantheon supernovae, and CMB lensing, of course. And once you include the ACT data, which takes you from the blue to the green, the big gain that you get, as has been emphasized, is in the timing, this critical redshift ZC. And if you look at the degeneracies in this enlarged model with this parameter C, basically by killing off regions of ZC, for example, kills off this high ZC region, kills off this preference for this additional low ZC region. It's killing off, in particular, well, it kills off both branches, actually, going to larger C values, but in particular kills off this region here of C positive. And it's sort of interesting if you look at S8, there's sort of this multi-island structure to parameter space here, which you can see the ZC posterior is sort of blobby. This SA H Naught panel, you can see this top left corner in blue, which is the fit to everything but ACT. Essentially, this is high S8, low H Naught, which is totally uninteresting for the H Naught tension. But it's a region of parameter space that fits the joint data set reasonably well. And it's this region of parameter space is just totally killed once you include ACT data. And that has to do with restricting the values of ZC and the correlations and degeneracies in the fit to the data with ZC. And then the final thing I'll mention is that we also looked at including the latest dark energy survey results And the basic punchline here is similar to in our previous analyses of the Dark Energy Survey year one with the EDE model, is that once you include this, the model becomes statistically quite happy with FED equals 0. And it does tighten the constraint on C slightly, in particular on the C positive branch, which, as I mentioned before, is correlated. You can see, for example, here, C positive is correlated with going to large values of S8, which can be understood pretty simply from this curve. Bumping up C bumps up S8. Okay, I just want to wrap up with my punchline again, which is that having a slightly negative value of C, which in physical terms mean the EDE field rolls down its potential and dark matter gets heavier at that same moment. That does help with the fit to both CMB and large structure data. But while you can get a good best fit, there's still no strong statistical evidence for this new parameter being non-zero. So we cannot reject the null hypothesis that this parameter is simply not there. And it's interesting to note that the region of parameter space, which is allowed by data, and the region of parameter space that helps you with resolving both H naught and S8, which is I floated negative C values, the values of C that you get is much less than what you would anticipate thinking about things like the Swampland distance conjecture.
Then they say C should be of order 1. 0.1 is of order 1, right?
Yeah, it depends who you're talking to. I would say, so here ES plus ACT is like 95% confidence is something like 0.05. So it's a factor of 20 away from 1.
I mean, compared to the other naturalness issues in standard model and beyond standard model thing,
it's very mild.
Yeah.
Right, so that's it for the details, and I'm happy to go into where to next.
Yeah, well, so I guess the where to next for everyone on the data side, maybe quickly first. What other than that you've already said, because I think there's obviously this better ACT data coming, and is there anything else that any of the three of you want to say on that data side, or do you feel that you've already said it?
Yeah, the next ACT data release is going to be spectacular, so stay tuned for that. Hopefully, time scale of order a year. That'll be called DR6. So stay tuned. It's going to be awesome. That's all I'm going to say.
Okay. Well, then on the theory side, Evan,
I guess so. On the theory side, for me, Colin briefly mentioned this coincidence problem of how does this new dark energy somehow know the time in which it has to be important. I think that's an open question. There have been papers on this. I think that's really interesting. I wonder and hope that has something to do with addressing electrical structure concerns. And something that I'm really interested in is if I think about EDE from a top-down framework, thinking about different quantum field theories or string theory setups, do those models have the same challenges? And then you would hope that in the top-down setup, you can start to answer questions about, is this actually fine-tuned? Because from the 4D perspective, it's hard to make any concrete statement about how finely tuned is something until you can see what is like the enlarged parameter space that this is actually coming from. Yeah, so I think these are all interesting things. I say, so one of the things I'm working on right now, which hopefully should be out relatively soon with a collaborator of mine, Marco, is top-down setup. Where exactly are these non-perturbative terms coming from? This cosine to the cubed, how exactly can that arise? And I think that's an interesting question. And once you grapple with that, that opens up doors to answer other questions.
Yeah, your comment that if somehow early dark energy is also influencing the matter power spectrum to fix the S8 problem, that does open doors then to making this non-fine-tuned. If it is somehow interacting with the matter, it might therefore, I don't know, you'd have to have it somehow interacting with hydrogen though, right? So that would be a bit weird, like for it to be crucial that it's happening just when the CMB forms. That's not a dark matter dependent.
Yeah, but the CMB forms shortly after maturation equality, and maturation equality is pegged pretty closely to dark matter.
Okay, so then the question for all three of you, what work being done in cosmology at the moment do you think is particularly underappreciated by the community?
I don't think this is underappreciated by the community, but I think what's going on for the early dark energy will happen with other kind of models. And since we will have access to very precise measurements from future data release from existing experiments or from Simon's Observatory or other experiments, we will need to look very carefully at the data in order to spot every deviation.
I mean, things can be appreciated but still underappreciated if they're still extremely important. So that's still a valid answer.
Yeah, I just want to sing the praises of our colleagues who have invested so many hundreds and hundreds of hours of their lives into producing these amazing data sets that we analyze. There's a huge group of people within ACT who understand the noise properties of our data. do a whole bunch of null tests, systematic checks of various kinds. And this work takes years and years to do. And none of this really exciting cosmology would be possible without them. So yeah, this praise goes out to all of our heroes in the time order data to maps side of things within Planck, ACT, SBT, the large scale structure surveys, everything. I mean, there's hundreds of people out there in the community doing this, and it's just absolutely crucial. So this goes out to all of them.
For me, what's underappreciated, I think, is one community. I think there's somewhat of a disconnect, at least in the H Naught portion of the cosmology community and the high energy theory side of the cosmology community. Which I think in the H Naught community, when we're thinking about EDE and we're taking these axion models, I think it's important to keep in mind the work that's being done to understand where axions come from. And there's a lot of interesting work happening there. And also from this, you can get predictions. So you can get a theory prior on what should be the axion decay constant. And if on the right here, I have the effective implicit prior on the axion decay constant coming from a uniform prior on FEDE, which is this hyperparameter, this derived parameter in EDE. If you impose priors on this derived parameter, what you're effectively doing is imposing this prior on the decay constant, which is peaked around the Planck scale. So I think it's important that cosmologists take input from high energy theory or theory proper and vice versa. Until relatively recently, the high energy theory side of the cosmology community hasn't really taken the Hubble tension seriously or to task. And I think this is one recent one that caught my attention, thinking about the weak gravity conjecture in EDE. And of course, there's our paper thinking about the Swampland distance conjecture and EDE. So I think that what could be really fruitful is putting together what we know from these two different sort of subfields. And I think hopefully that will lead us to, one, a model which does fit all data sets, so I really do restore cosmological concordance, and then we can learn something about fundamental physics. So I think it's an exciting time to be working on this.
Awesome. Thanks everyone for watching. If you like this, please do subscribe and click the bell if you want to be notified, and click like to help with YouTube algorithms and all that. If you have any questions or suggestions, leave a comment. Check out Colin's earlier talk, which is probably appearing on the screen somewhere at the moment. And thanks, Adrien, Colin, and Evan, for the great talks.
Thank you, Sean.
Thank you.
Thank you.